In this video, we are asked to show that the integral of 1 divided by a plus b cosine of x squared dx is equals to this guy. So we are asked to prove that this integral is equals to the answer on the right hand side. And the condition is that a and b are both greater than 0, that are positive values. So I'm going to solve this one using a very important substitution, which will be important in evaluating trig integrals. So let's start off by calling our integral I. So I'm going to let I will be equal to our integral, the integral of 1 over a plus b cosine of x squared. So this is what we have, and then we now have, so recall that we know that the cosine square of x, this one can be written as 1/2 into 1 plus cosine of 2x, right? So this is what we have. We can just plug that into our integral. So our integral I is going to be the integral of 1 all over a plus b, and then cosine of x squared, that one can be replaced with 1/2 into 1 plus the cosine of 2x, like this, and then dx. So I'm just replacing cosine square of x with this guy. And now what do we have? We have the integral of 1 divided by a plus, you can bring 1/2 out here, then you multiply b through, and that is going to be equal to b plus b cosine of 2x, like this, and then dx. So what can we do to eliminate the half at the bottom? So I'm going to multiply the numerator and the denominator by 2. When I do that, the numerator becomes 2 on top here, and the denominator becomes 2 times a, which is 2a, plus 2 times half here, that is going to be 1. So that is going to be left with b plus b cosine of 2x, like this, and then dx. 2 is a constant, it comes in front of the integral, and you have 1 all over 2a plus b. I'm grouping this one as a constant, and then b cosine of 2x, and then dx. Now I'm going to do a substitution here. So the substitution is that I am going to let y, let's say, to be equal to tan of x. This is very important in solving many trig integrals. So let's do something here. So we can find an expression for dx, right? So when y is equals to tan of x, that implies that x is the tan inverse of y. And we can find an expression for dx. So dx dy is going to be differentiating tan inverse of y is 1 all over 1 plus y squared. So that implies that we can replace dx in our integral with 1 all over 1 plus y squared dy, that we can plug into our integral. Now let's find an expression for the cosine of 2x in terms of y. If we are doing that, we have to draw a right triangle here with our right angle here, and our angle here. So we are using this one, y is equals to the tan of x. So the angle here is equals to x, right? So I'm going to put x here. So tan of x is opposite over adjacent. This y is the same as y over 1, right? So the opposite is equals to y, and the adjacent is equals to 1. We now have to find the hypotenuse, that is the line opposite to the right angle, the hypotenuse. The hypotenuse is the sum of squares of the other two sides. So that is the square root of the sum of squares of the other side. So the opposite squared is y squared, and the adjacent squared is 1 squared, which is 1. So the hypotenuse is the square root of the sum of squares of the opposite and the adjacent. So this is what we have for our right triangle. And now we can find sine of theta from that, sine of x, I'm sorry, from this right triangle. So sine of x is opposite over hypotenuse. Hypotenuse is the square root of y squared plus 1. We can find cosine of x. Cosine of x is equals to adjacent, which is 1 over hypotenuse, the square root of y squared plus 1. So this is what we have. And now we can find an expression for cosine of 2x in terms of y. We know that cosine of 2x, changing colors here, cosine of 2x is the same as cosine square of x minus sine square of x. That is from the double angle identity. So this is equals to cosine of x is this guy here. So that is 1 all over the square root of y squared plus 1 We have to square that because it's cosine squared minus sine squared, which is y all over the square root of y squared plus 1. Square this as well. So that implies that the cosine of 2x is the same as squaring this is 1 all over y squared plus 1 minus squaring that is y squared all over y squared plus 1. And combining this, we have 1 minus y squared all over 1 plus y squared because they have the same denominator. So I have expressed cosine of 2x in terms of y like this. This I'm now going to replace in our integral. So coming back to our integral here, we have I to be equal to 2 outside the integral of 1 all over 2a plus b and then plus b times cosine of 2x. That is what we have here, b times cosine of 2x. And cosine of 2x is the same as this guy. So I'm going to replace that with 1 minus y squared all over 1 plus y squared like this. And then dx. An expression for dx in terms of y is 1 all over 1 plus y squared dy. 1 all over 1 plus y squared dy. So this is what I have. Our integral is now entirely in the y world. So this is 2, the integral of 1 all over 2a plus b. And then I have to multiply that one by 1 plus y squared. I'm just multiplying by the LCM 1 plus y squared. And then plus b into 1 minus y squared. All this one divided by the LCM 1 plus y squared. Times 1 all over 1 plus y squared dy. Cool stuff. Now this one is going to cancel this one. Now we have I to be equal to 2 times the integral of 1 all over. Now let's FOIL these guys. So that is going to be 2a plus 2ay squared plus b y squared. And then expanding this one is going to be plus b minus by squared like that, and then dy. So I is going to be 2 times the integral of 1 all over some things will cancel. This by squared is going to cancel this negative by squared, and then you have b plus b, which is 2b, and then it's 2a plus 2b now, and then plus 2ay squared. This is what the denominator is left with. 2 is constant across all the terms in the denominator. We can factorize that one out, and that will cancel the 2 out here. So the integral is just left with the integral of 1 all over a plus b here, and then plus ay squared dy. This is what we have left. Now to make these things clearer, we have to divide the numerator and the denominator by a. So this is 1 all over a, and I'm going to do the same thing to the denominator. A plus b plus a y squared all over a to maintain equality. So 1 over a is a constant. It goes in front of the integral. The integral of 1 all over, this is now left with a plus b all over a, and then plus y squared. That is a y squared over a is y squared, and then dy. Now we can compare this one to the arctan integral. Let me rewrite it here. This is 1 over a, the integral of 1 all over y squared, plus this one can be written as a plus b all over a. All this one squared in a square root like that, and then dy. And now let's compare this one to the arctan integral. The integral of 1 all over a x squared plus a squared dx. This is the same as 1 over a, and then the arctan of x over a plus the constant of integration. So this is the same as the arctan integral. So I is going to be equal to 1 over a. Now solving this integral, we have 1 all over a. A here is the square root of a plus b over a, and then times the arctan of x over a. X here is y over a. A is the square root of a plus b over a, like this. So this is what we have. Now we have I to be equal to, now taking the reciprocal of this is going to be 1 over a times the square root of a over a plus b, like that, and the tan inverse of the same thing here, taking the reciprocal of that is going to be the square root of a over a plus b. times y, like this. But recall that y is equal to the tan of x. That is our initial substitution. That is the substitution that we used. Y is equal to the tan of x. So just replace y with tan of x, and then you can wrap up the integral by doing simple algebra. So this is 1 over a, and then this can be written as the square root of a over the square root of a plus b, and then the tan inverse of the square root of a over a plus b, and then replace y with the tan of x, our substitution. Here we can do some rationalization. We have 1 over a times the square root of a. I'm going to rationalize by multiplying by the square root of a and doing the same thing to the denominator, square root of a, and then the tan inverse of the square root of a all over a plus b tan of x. So this is 1 over a times, this is multiplying to a, so 1 over a times a is just 1, and that will be left with 1 all over the square root of a times the square root of a plus b, and then the tan inverse of the square root of a all over a plus b tan of x, like this. And therefore we can now wrap up the integral with what we have initially. So multiplying in, we have 1 all over the square root of a times a plus b, because they are all having the same square root, to put them in one square root. And then the tan inverse of a all over a plus b times the tan of x, like this. So this one is the proof that we are required to find. So if we go back to the very top, you will see that that proof is the same as this one, and this only works for a, b greater than 0. Both a and b are greater than 0. So that is how to solve this kind of integral. So if you are given any positive values of a and b, you can just plug them into this proof here, and then you find the integral of this integral. So this is how I can solve this integral. If you know an alternative version to solving this which is quite faster than this, I would ask you to put your comment in the comment section and let's get talking. I thank you so much for watching this video. If you like the video, please give me a thumbs up and subscribe to Calculus Diaries for more engaging content. I thank you, and I'll see you in the next one. Bye bye.